Hello everyone and welcome to this video. Today I want to show you how to solve a truss like this. When you look at the problem, I want you to note a few things. First of all, look at the external loads. Make sure that you're aware of all the external loads on the problem. We have 3 kilonewtons on joint E, 6 kilonewtons on joint B. We have the geometry we need. Just make a quick check that you can get all the angles because we will definitely need them. And then check for the supports. So let's look at joint A. What type of support is this? This looks like a hinge support to me. And hinge supports take 2 reactions. If you look at joint C looks very similar. Like, you know how you would usually expect like a roller here and a pin support here. This problem is interesting because it has 2 hinge supports, 2 pin supports. This means that joint C has 2 reactions as well. And when you do a quick count of the unknowns, 2 unknowns here, 2 unknowns there, that seems to be 4 unknowns. That's too much. We only have 3 equilibrium equations. So is this problem statically indeterminate? Are we going to struggle calculating the reactions? The answer is no, because joint C is very interesting. There is just one truss member or link member connected to it. We know that truss members, they have just one force in it. So this one force will make it very easy to calculate this reaction. So before we draw the free body diagram, I want you to understand something. When you have a link member connected to a hinge support or a pin support, there is only one reaction in the direction of the link member connected to the joint. So if you don't understand me or if you don't believe me, let's try to work it out for ourselves. I like to take a imaginary scissors, think of imaginary scissors, and isolate the reactions and the joint at C. So I'm going to take a dotted line. I'm going to go completely and surround the joint. And once I intersect with the truss member, I'm going to interrupt it. And I'm going to have to replace it with a force. So I will take joint C here. I will put joint C here. The force that I intersected here, I will assume it as tension. And I will explain to you why I like to assume new forces as tension. I will assume 2 reactions at C. So a force, let's say I will put a force here and we'll call it C X, and a known force here and we'll call it CY, and this is joint C. Everything here inside of this dotted line, I have it here in the free body diagram. So there is just one member and there is 2 reactions. If you do a quick check for the summation of forces in X has to equal 0 and the summation of forces in Y has to equal 0, you will realize that in the Y direction, CY is the only force. There is no force in CY, so therefore CY has to equal 0. And the only reaction here is CX. If this is force CD, so we pretty much know that in the summation of forces in X equation, CX and positive X plus CD has to equal 0. And this automatically shows us there is value for the reaction in Cx, and there is a relationship with the force in CD. So they're equal and opposite. When you get this term here, you will figure out that Cx equals negative CD. So what I want you to understand here is when there is a link member, just one force connected to a pin, this will make things very easy, and this provides a reaction in the same direction as the link member. So there will be a reaction here, and we will call it Cx. This is the regular pin support. It will have two reactions, so I will give it an AX in this direction, and I will put AY in this direction. So a quick question: why this joint, which has a pin support, got two reactions, AX and AY, and this got only CX? The answer is there are two members here connected to the pin, therefore it's a normal hinge support or a normal pin support. The problem here, or the easy part here, is there is just one link. There is just one link. If you study the stability or the free body diagram of joint C, you will realize the only force in the Y direction is the reaction CY. That's why it's 0. The summation of forces in Y has to equal 0. That's why CY equals 0. And the only value for the reaction is CX, and it's actually related to the force CD. All right. So as usual, first step, we will have to figure out these reactions. So how do we do that? I want you to draw a pretty rough free body diagram for the entire truss. I don't need you to do it in too much details. If you want to just quickly add the members, that's fine. This is the free body diagram of the entire structure. I have no supports here. I have nothing. I just started with the overall geometry or the overall outline of the truss. Second, I want you to put all the important external forces. So don't forget to include 3 kilonewtons here. So this is 3 kilonewton. Is there any other external forces? There is 6. So I'm going to put 6 kilonewton. And this is pretty much all the external load. Don't forget to include the reactions. So I'm going to put the reaction, I call this one AX, and a reaction AY. There is also a reaction CX, and I just explained why there is just one reaction here, because the CY equals 0. All right, so I like this very much because it has only 3 unknowns: AX, AY, and CX. So what are the equilibrium equations we have for this stress? So I like to make sure I included everything. So everything in this dotted line is in equilibrium. And that gives us 3 equilibrium equations. The summation of forces in X has to equal 0. The summation of forces in Y has to equal 0. The summation of moments about any point has to equal 0. The reason why these equations are true, because this truss is in equilibrium and it's stable. It's not going to move in X, it's not going to move in Y, and it's not going to twist, it's not going to rotate about any point. It cannot rotate about any point because it's stable. It's not going to rotate. So I like to start with this equation over here, the moment equation, and let's do it with taking the summation of moments about the point with the most number of unknowns. So where is the point with the most number of unknowns? Where are the unknowns to begin with? Well, we don't know the reaction. AX, AY, and CX. So we might as well start by taking the summation of moments about joint A. So let me start with the first equation. I'll call it equation 1, which is the summation of moments about A has to equal 0. So what are the forces that cause rotation about A? In order for you to do that, it's very simple. Just put your finger at the point of rotation and then observe what are the other forces that cause rotation and what's the direction of rotation. So I mentioned the right hand rule. If you put your right hand over your watch and see what counterclockwise direction is, you'll see that your thumb is up. So I will consider rotation that is counterclockwise to be positive, and I will consider clockwise rotation to be negative. These are my assumptions. You can follow them if you like. If you want to have a different assumption, just make sure you're consistent throughout your answers. So this way the numbers don't contradict each other. So I'm going to put my finger here and I'm going to take the moment of the 3 kilonewton about A. So moment is force times distance. So I need a force and I need a distance. And it's not just any distance, it's the perpendicular distance. So how do you get the perpendicular distance from point E to point A? What I like to do is extend the force on both sides. So I'm going to extend the force all the way up, extend the force all the way down, and now I need to go from the point of rotation perpendicular to the line of action of the force. And you will very quickly realize that this distance here is the distance perpendicular to the line of action of 3 kilonewton, and this distance happened to be 1.2 plus 1.2, which is 2.4. So I will very quickly take the equation of moment. The last thing I want to know about the moment of 3 kilonewton, is it rotating clockwise or counterclockwise? So what I'm going to do is same thing, put my finger on AX, and then I'm going to put this pen here and push on it in the same direction as this 3 kilonewton and see what is the direction of rotation. And you will notice it's rotating like that. Is this clockwise or counterclockwise? This is clockwise. That's why it's negative. So I will start by negative 3, that's kilonewton, multiplied by 2.4. This is in meters. And that's pretty much the moment of 3 kilonewton about A. I'm going to do the 6. It's rotating in the same direction, so it's negative as well. The force is 6 kilonewton, and the distance now, the perpendicular distance, is 1.2. So I will multiply this by 1.2 meters. So look at the free body diagram. Put your finger on the point of rotation. Is there any other force rotating about A? Yes, CX, and it's actually rotating the opposite direction. So it's rotating counterclockwise. That's why it's going to be positive CX. We don't know how much is it, but that's fine. The equation will figure it out. I need to know the perpendicular distance between the reaction CX and the point of rotation A. So let's do the same exercise. I want you to extend the force on both ends. Extend it all the way here, extend it all the way there. Now go from the point of rotation perpendicular to the line of action of the force, and you will very quickly realize that this distance is the perpendicular distance, which happened to be 0.9 meters. So I'm going to very quickly multiply this force by 0.9. This reaction is going to be in kilonewtons, and this distance is in meters. And is there any other force that is causing rotation about A? Well, good question would be like, what about AX and AY? What's the moment of AX about A? The answer is 0, because this force is passing through the point of rotation. It has no perpendicular distance. It's just the force applied at the force, at the joint. And this is why AX and AY, they have no moment about A. So I don't have to account for them here in the moment equation. My question to you now is, what happens when I add all these moments? Because the truss is in equilibrium, the summation of all these moments has to equal 0. So let's do a quick math. If you crunch the numbers, you will very quickly find the force CX. So I did the math, and you will see when you do this side and bring it to the other side and then divide by 0.9, you will figure out that CX is positive 16 kilonewton. The reaction, the units are worth marks, so remember to ask yourself, is this kilonewton, is this newton? And now I want to ask you, what does this positive sign mean? That means that this direction that I assumed is correct. So because it's positive, then CX is actually looking in this direction. So what happened if the 16 was negative? It was negative, CX was negative 16. That means CX is actually not looking this way, it's looking the opposite way. So you can either go ahead and change this direction and flip it and use the positive magnitude, or you can keep the arrow with the negative. So both ways work. You will have to make sure that you can get the correct final answer, and whatever method works for you, you can keep on using it. So I'm going to note here that CX equal 16 kilonewton in this direction. This direction is very important. All right, so now this equation is gone. We have two more equations to go. So it seems that the summation of forces in Y would be a good thing to do. So let's do equation 2, which is summation of forces in Y has to equal 0. So let's look at all the forces going up as positive minus all the forces going down as negative, and this has to equal 0. The only force going up is AY. The force going down is negative 6 kilonewton and negative 3 kilonewton. When you do the math, it has to equal 0. So we'll do just quickly the math, and this will result in AY. You will find that it will equal positive 9. So what's the unit of this force? Is it newtons? Is it kilonewtons? The answer is kilonewtons. Just like this force here, just like these forces. So the forces here will be in kilonewtons. And the positive sign means that this direction is correct. So I will just note that AY will equal 9 kilonewtons. This leaves us with the third equation, which is the summation of force in X has to equal 0. All the forces in X, positive X, minus forces in negative X, this will has to equal 0. So I will go ahead and put AX, I assume them going positive, plus CX going positive as well. There is no other forces in X, so just adding these two have to equal 0. But remember that CX is actually 16 kilonewton and it's going in this direction. So in order for this to equal 0, this means that AX is actually negative 16. Negative 16 kilonewton. So what does that mean? What does that negative sign mean? It means that AX is actually not going this way. It's going the opposite direction. So if you want to keep the arrow like this, the magnitude of X, AX, has to always be negative 16. But what I actually like to do, I like to consider the positive magnitude and the correct direction of the force. So I will just like very quickly cross that direction and put this direction here and call this 16 kilonewton. So I will use the correct arrow with the positive magnitude, or if you wanted to use this, then you will have to use the sign. It's up to you what you decide to use for your answer.